Alright, in this chapter we're going to spend some time examining the exponential logarithmic functions, and we'll begin with exponential functions. Now, we might already be familiar with functions that look like, y equals x squared or y equals x cubed. We call those power functions, and their basic, form is that the base here is variable, right? We've got x and then raised to some constant power. The y equals x squared, that's the function that just tracks what happens when we square different numbers. Now, with exponential functions, we kind of switch that around, and we take a look at a constant base and raise it to a variable power. So the exponential functions kind of have this basic form. Some base, which we call b, that's a constant. That's just a positive number that's not equal to 1, and then see what happens when we raise that to different powers. So the exponent is the variable. The reason that it's not equal to 1, the reason that we require the base not be equal to 1, is that 1 raised to all the power, any power is just 1, and so if your base is 1, it's just a constant function, which is boring. It's not actually exponential. So, for example, here's a list of some exponential functions. 2 to the x is an exponential function. 1.3 to the x, 2/3 to the x, those are all exponential functions. In fact, I'm going to add one more. Like those are all written in that form of that positive base to a variable power. But I could have something like 3 times 2 to the x. And that's also exponential. I mean, it has that form, right? It has this part here that's important for being exponential. It involves this, some constant raised to a variable power. We've spent some time working with exponents and rules of exponents, and we will find it helpful and handy to keep some of these properties on hand. First, a to the negative n, a negative exponent. Remember, that means that we're just going to throw that in the denominator. So a to the negative n is equal to 1 over a to the n. A to the 0 power is 1. Anything raised to the 0 power is 1 as long as that base is not 0. And then here's how we define rational exponents. If I'm raising a to the n over m power, the numerator tells me what power I'm raising a to, and then the denominator tells me what root I'm taking. So we're going to get a sense for the behavior of these exponential functions. We're going to plot some graphs. So I'm going to we'll start with y equals 2 to the x. And what I've done here is I'm making a table, and I've listed just some values of x here on the left side in the first column, and I'm just going to track what the output values are. So we'll start here. If x is -2, then this function is 2 to the -2. We know that's 1 over 2 squared, or a quarter, and that'll give us the point -2 is x and 1/4 is y. On the next one, 2 to the -1, that's 1/2. So we have the point -1, 1/2. When x is 0, we've got 2 to the 0, which is 1. So that gives us the point 0, 1. And moving on, 2 to the first is, of course, 2. So we get the point 1, 2. Next, 2 squared is 4, so we get the point 2, 4, and 2 cubed is 8, so we get the point 3, 8. What I've done, in the left side, that first column, I just chose a variety of x's. I made sure that I got some negative values, some negative x's, some positive x's. It's always helpful to see what happens when you plug in 0, I think, as long as as long as you're allowed to plug in 0. So now we can plot these points and sketch a graph. So -2, -2, 1/4. I'm going to start at the top. -2, 1/4, I guess that'd be about there. Negative 1, 1/2 would be there. 0, 1, 1, 2, 2, 4 would be there. And then 3, 8 would be there. And so now when I'm sketching a graph, you know, I'm trying to use the points to observe a pattern. This is a curve, right? So I'm not doing connect the dots with a bunch of straight line segments. I am observing the pattern here and sketching a curve that goes through all of those points. So it looks something like that. And now as x gets bigger in the positive direction, I know like 2 raised to bigger numbers, that's just going to blow up. That's going to get huge. Over on the left side, if I keep plugging in bigger negative numbers, then what'll happen is it'll just get smaller and smaller. You know, that you're not going to raise a positive base to any real number power and get a negative. So this never actually becomes negative, it never actually becomes 0, but it'll keep getting smaller and smaller. So we kind of have this J shape to the graph. Now the next function that we're going to sketch on the same set of axes is 1/2 to the x. And before we do that, I'm going to do a little bit of work in the margin. And let's remember another rule of exponents that says if I have a fraction that I raise to a power, then I could take the top to the power divided by the bottom to that power. And so now what we have is 1/2 to the power x. So that's 1 to the x over 2 to the x. Of course, 1 raised to any power is 1, so I get 1 over 2 to the x. And now we know from our negative exponents rule that 1 over 2 to the x is equal to 2 to the negative x. Now we could, use the function in this form, 1/2 to the x, but if we use 2 to the negative x, we can actually kind of reuse some of the values, that we've already found for 2 to the x. So I'm going to rewrite this as 2 to the negative x. So what we're going to do when we find the y coordinates here is we're just going to change the sign of x and put that up as a power on 2. So when x is negative 3, we're finding 2 cubed, 2 to the positive 3, and that's 8. So we get the point negative 3, 8. When x is negative 2, that means we're going to find 2 squared, which is 4. That gives us the point negative 2, 4. And when x is negative 1, we have 2 to the first, which is 1. Which is 2. And that gives us the point negative 1, 2. When we plug in 0, we're just finding 2 to the 0 power, which is still 1. So this goes to the point 0, 1. And let's see, next, when x is 1, we're finding 2 to the negative 1, which is 1/2. So this goes through the point 1/2. This goes to the point 1, 1/2. When x is 2, we're finding 2 to the negative 2. So that gives us 1/4, right? 1 over 2 squared. This gives us the point 2, 1/4. Now we can plot these points. So I got negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, and 2, 1/4. We get a similar shape, it's just kind of backwards, it's flipped around. Alright, so we know that if we keep going in the negative direction, it'll blow up. If we keep going in the positive direction, it'll get smaller and smaller because we're raising 2 to bigger negative exponents. So this one, I'm just going to label them. This is 1/2 to the x, or 2 to the negative x. The first one, that's 2 to the x. And now we have one more to do. Now, before we do the third one, I might just, notice these two graphs, it's not just that they have opposite behaviors. They're really complete reflections of each other. That has to do with their bases. I'm actually able to write them both as 2 raised to a power. I've got 2 to the x versus 2 to the negative x. But just generally, when that base, if I think of it as the fraction to the x power, like 1/2 to the x, or if I have a base bigger than 1 to the negative x power, that overall gives us this behavior, what we call an exponential decay. It's something that gets small as x grows in the positive direction, right? So the bigger x is in the positive direction, the smaller that value is. And this function in black, 2 to the x, so I have this base bigger than 1, raised to the x power, that's an exponential growth function. As x gets bigger in the positive direction, it grows. That function blows up. So let's do one more. We've got one more graph to plot here. We're looking at y equals 3 to the x. So again, I've got a variety of values here. When x is -2, we've got 3 to the -2. Now that's 1/3 squared, or 1/9. That gives us the point -2, 1/9. When x is -1, we have 3 to the -1, and that's 1/3. So -1, 1/3. When x is 0, we get 3 to the 0. That is, of course, still 1. So we got the point 0, 1. Again, so we see that point appearing on all 3 of these curves. Then 3 to the first is 3. Get the point 1, 3. 3 squared is 9. That gives us the point 2, 9. 3 cubed is 27. So we have the point 3, 27. And then we just want to plot these and again sketch this curve. Now my y-axis doesn't go quite high enough, so I'm not going to include the point 3, 27. That would kind of be off the page even. But I can plot the rest of these. So let's see. We have -2, 1/9. That's just super tiny. -1, 1/3. That's a little less than 1/2. Whoops. Whoops. And it goes through 0, 1. It goes through the point 1, 3. And it goes through the point 2, 9. All right, so maybe some observations we can make here, right? So the one in green, that's 3 to the x. Some observations we can make here is that, we have a positive, a base that's bigger than 1. That base is 3. So just like 2 to the x, that gives us the exponential growth behavior. Now, it grows faster than 2 to the x, or appears to, right? As when x is bigger than 0 for the positive values, that green graph is always above the black graph. So it seems to be growing faster. But on the other side, on the negative sides, it gets smaller faster too. For the negative values of x, the green graph is always below the black graph. And we can summarize, just sort of list some of the observations that we've sort of already been making as we've discussed this. All of these graphs, as long as it's the form b to the x, so it's not like some constant times b to the x, but just some base raised to an x power, those will all pass through the point 0, 1, because any non-zero base raised to the 0 power is 1. They're all these sort of continuous, like nice and smooth, J-shaped curves. No holes or jumps. The x-axis is a horizontal asymptote, and that asymptote just means it's a line that it approaches. So up here, that just means that we see how the graph, whether it's an exponential growth or an exponential decay, that graph approaches the x-axis as x moves larger in one direction or another. If the base is bigger than 1, then y increases as x increases, right? This is what we called the exponential growth. So that's 2 to the x and 3 to the x. And if the base is a fraction, like between 0 and 1, then y decreases as x increases. This is the exponential decay. So that exponential decay, that was the 1/2 to the x that we did on the last page. The exponential growth, those were the graphs of 2 to the x or 3 to the x that we did on the last page. Now, in working with exponential functions, one base that comes up over and over again is called the natural base, or Euler's number. We just call it e. It's a number kind of like pi. It's irrational, it's transcendental. We can't write out all of its digits because it goes on infinitely with no pattern. So for that reason, we just abbreviate it and call it e. It's approximately equal to 2.718. And it is one of the most important numbers, one of the most fundamental numbers in all of mathematics, with exponential growth or decay like applications that occur in nature. You see this base used a lot. So any kind of exponential growth function or exponential decay application can be written in this form. Even one where you've used a different base, right? Like if I had some, like, I don't know, y equals 2.8 to the x or something, or y equals, 1.3 to the x. There's a way you can write it, rewrite that function with a base e. And a lot of the mathematics that we do with exponential functions just becomes more convenient when you use the base e. We'll see some examples of working with this, and it'll become way more apparent. If you go on to take calculus, it'll become a lot clearer why we prefer this base e over other bases. But for now, just note that, e is a number between 2 and 3, right? It's about 2.718. So if I were to sketch a graph of e to the x, if I were going to try to do that, I'll just note that it's going to lie between the graphs of 2 to the x and 3 to the x, because e is between 2 and 3. And in fact, e is about 2.718, so it's actually closer to 3 than it is to 2, and you'll note that that graph of e to the x is closer to 3 to the x than it is to 2 to the x. So exponential growth and decay applications abound in nature and in like finance and a lot of situations, chemistry and physics. So these functions, these situations are usually modeled with an equation or a function that looks like that. We have some quantity a naught, like a naught would be some constant, and then times e to the kt. So where e is Euler's base, and we have some constant k that's specific to the problem. It has to do with the rate of growth or decay. If for an exponential growth application, an exponential growth problem, k is positive, right? That coefficient on t in the exponent would be positive. Exponential decay problems, in those problems, k is negative, so you'd be raising e to the negative, kt, negative exponents. So we're gonna close out this section just by doing an example. Here's an exponential growth problem, and it says a bacteria culture grows exponentially according to the equation n equals n naught e to the 0.4581 t, where n naught is the initial number of bacteria and n is the number of bacteria after t hours. So this is a function that spits out a value n. It spits out how many bacteria are present after t hours if you know the initial amount of bacteria you have, and you know what time you're looking at. So n naught is the initial number of bacteria. That just means the number of bacteria at time equals 0. Now, in this problem, they say we start with 1,000 bacteria. So that means n naught is 1,000. we want to know how many bacteria to the nearest whole number will be present after 6 hours. So we want to find n when t is equal to 6. So here's our function. Here's our function that models this. N naught times e to the 0.4581t. I know that n naught is 1,000, and we want to know how many are present after 6 hours. So I'm going to plug in 6 for t. And here we really just have to turn to our calculators to help us out. So I'm going to open it up. That's going to take a few seconds on this machine. All right, so you'll notice, we have a button to call up the number pi. Pi is a special number, so we make sure we use the button instead of approximating with 3.14. We're doing the same thing with e. All right, we are not going to approximate e with 2.718. We're going to make sure we use the e button on our calculator. There's two ways that you can access the value e on your calculator. One is the divides key. You can see in blue it says e. So I could just do, say, e squared by doing a second divides to call up e, and then squaring that. Also, over on the left side, next to the 4 button, there's the ln button. That's a natural log, and we'll talk about that in the next section. But above that in blue is e to the x. If I use that, it's waiting. It calls up e, and it knows I want to put in an exponent. So either of those ways to call up e is fine. What I want to do is compute 1,000 times e raised to a power. So I'm going to do second ln. And then up here I've got 0.4581 times 6. And I get 15,620.75. And we want it to the nearest whole number, so I'm going to say 15,621 bacteria after 6 hours.